Welcome to the third module. The first session of the third module basically deals with hardware in loop for power systems. So in this session, I'll be discussing mostly about the need for real-time simulation, the challenges in real-time simulation, benefits of real-time simulation, and what exactly is real-time simulation. So basically, the outline of this session is as shown in the figure. So first starting with benefits of real-time simulation. So let's discuss about the different challenges first we face in power systems. So due to the advancement of technologies, there are a lot of challenges that comes into our existing infrastructure of power system networks. So to start with, like we can talk about integration of renewable energy, electric vehicles or heat pumps in our electrical networks. Then the different sources of communication that are being introduced nowadays so that we can communicate with intelligent devices like RTUs, IEDs, PMUs. So various protocols that are being introduced. So how to integrate those protocols in our existing infrastructure. Then the new converter topologies that are coming into picture right now, multi-level converters, modular multi-level converters, MMCs. So there are various kinds of fax devices that are being developed. How to integrate all these challenges and come over with the best solution so that we can achieve the maximum efficiency of our existing infrastructure. So the one and only solution that we find for all these challenges is simulation. So why we actually go for simulation? What is simulation? Simulation basically means to mimic the operation of an actual object, like the real object we are just trying to mimic is operation. So what are the benefits of doing simulation, the goals of simulation? So in simulation we basically want to reduce the delay, the risk, and increase the cost efficiency. So the various tests that can be done during simulation includes as follows. So if you go, if you are designing a particular algorithm, okay, so before testing on an actual device, people prefer to test it on a simulation platform, for example, MATLAB. So we design an algorithm, we perform multiple tests on it, and before actually doing a hardware prototype of it, we carry out thousands and thousands of tests so that we can come up with the best solution. So in this way, like we don't have to means we don't have to spend a lot of time on it. Okay, we don't have to prototype the hardware again and again if we are doing some mistakes. So it is easier to do as well. Now, like there are various tools that allow like early detection of errors. Okay, so we can actually overcome a lot of errors. We can actually use the same simulation platform for multiple applications, not just like once you have done with your power system models, you can again work with electric vehicle application, you can again work with power electronics application. So the same tool, same platform can be used for versatile applications. Now, as I said, the different benefits of simulation, the goals of simulation is to reduce cost, reduce delay, and reduce the risk. So reduce cost, no need for a real-time prototype, detect faults earlier, then minimize the malfunctions after installation. Talking about the delay, so how can we reduce the delay? We can develop independently the hardware and software of a controller. For example, so we are working on a relay prototype. Okay, we want to test the relay with a particular power system network. So we are introducing a fault in the power system network, the voltage and currents we are monitoring, and we are giving it to the relay. So now we can actually take a hardware relay, we can then test it with a simulated virtual power plant network. Okay, so we can develop a hardware separately, we can test the hardware separately with a software platform. Now we can test systems independently in lab, we don't have to go to the field with the utility. Okay, inside our lab we can get a relay, we can develop a virtual power plant network, and then we can test on it, we can perform multiple tests. Then how to reduce the risk? Yes, obviously there will be a lot of reduction in risk. Why? Because when we are talking about power system, there are a lot of risk factors included in it. If you are working on a particular protection algorithm and we want to test it for a particular, suppose, overcurrent fault, we cannot directly go to a utility and ask them, we have designed a algorithm for overcurrent protection, please test it with your utility. Then they will obviously say no, because like the overcurrent algorithm may be correct, may be incorrect. So in case it is incorrect, then the isolators, the breakers, the transformer may get affected, the insulation may fail. In that case, there will be a lot of losses happening. So there is a lot of risk in that. So we can avoid all those risks. We can just simulate a power system network, and we can actually develop the entire protection algorithm with respect to that simulated power system network. The next is the model based design. Basically, model based design is just a namesake. We only will be discussing about the need for real time simulation. How we actually go from simulation to real time simulation. So the first step in performing the simulation is like you have to design a model. In the previous sessions, you must have gone through various application how to perform means design a power system network. So let's take the simple example of a 9-bus system. So if you are designing a 9-bus system with the help of a MATLAB model, MATLAB Simulink library, so that is your first step. So you design your MATLAB model in offline mode in your Windows environment in your MATLAB Simulink library. So after it is done, the next step is using a real-time platform. So OpenRT is a company which develops real-time simulators. So we can actually take this Simulink model and then actually burn this Simulink model on a real-time platform of OpenRT. So this real-time simulator will be providing us real-time results. Then we'll be able to say, like as I said earlier, like the protection logic or the protection algorithm that we want to test with a utility, we have actually tested in a real-time environment and the results have been validated. Now, what is the next step? The next step is like hardware interfacing. So this is exactly a closed loop performance we are going to do. So we are taking a MATLAB model, we are burning it on a real-time platform, then again we are taking out results and giving it back to the MATLAB environment so that we can actually tune the parameters on the fly. For example, we want to introduce a fault at t equal to 10 seconds. Okay, then we want to monitor whether the relay is properly functioning or not. So what we will do, we will take the voltage and current results from the real-time model which is running on the real-time platform. We'll send it to a relay, the hardware relay. Then the hardware relay will actually give a trip signal based on the voltage and current commands that it has received from the real-time simulator. Then this trip signal will go back to the MATLAB model so that the different types of breakers or isolators connected across the power system network will receive the trip signal and it will isolate the faulty section from the live section of the model. So this is basically what I said, like model based design. So we design a model, we burn it on a real-time platform, we interface with the hardware. So there are various applications which we can actually develop on this real-time simulators, be it mechanical application, be it electrical drives, be it power systems, powertronics, aerospace, any kind of application can be developed on this. But this session mostly will be dealing with microgrids, power system networks, transmission distribution. So we'll be dealing with all such applications. Now, there are various stages while performing real-time simulation. So the first stage is model in the loop. So this model in the loop is nothing but the model that we design on our simulation platform. So later on the session, I'll show you how to work with a Simulink model for a real-time platform. But the first step which I'll be referring to is model in the loop. So in model in the loop, we'll be actually dealing with the proof of concept. Like we design a power system network, we introduce a fault, then we make a relay logic in the same platform simulation environment and test the protection logic with that particular power system network. So this actually proves our concept that we are going to implement something which actually is going to be a hardware prototype at a later stage. So proof of concept, then this is also known as the preliminary design stage. So as you can see from the figure, there are two PCs involved here. The first PC is where I am saying you will be having your MATLAB model, that is called as a host PC. Then there will be another PC, that is the real-time simulator. The simulator is nothing but an PC. Okay, it also comprises of certain processors, certain cards. Okay, so I'll be talking about the hardware architecture later, but as of now we need to remember like there will be two PCs involved over here. One will be called as a host PC and the other will be called as a target PC. Now the host PC will be containing a MATLAB environment. The target PC will be running on another operating system known as real-time operating system. Okay, so we'll be having a simulated plant controller designed on our Windows MATLAB environment, but it will be running actually on a simulated platform, the real-time simulation platform. So this is the first stage. Now, the next stages can be of two types. So the first type is rapid control prototyping. So when I'm talking about simulation, so in simulation, basically we deal with a plant and a controller. Now, when I talk about rapid control prototyping, what exactly it means? Figure depicts all. So the figure shows like one simulated controller is being designed inside the virtual platform and there is a real plant with it. So rapid control prototyping means we'll be having a controller inside the real-time platform and we'll be having an actual plant, be it a motor, be a PV, be a windmill, anything. So we'll be interfacing a controller with this real plant. Now, the other perspective can be called as hardware in loop. So what is hardware in loop? Again, the figure depicts it all. So here we'll be designing a simulated plant and we'll be interfacing it with a real controller. So the plant will be inside the real-time simulator and the controller can be real or it can be another real-time simulator. So choice is on you. Now, so let's come back. Now we understood what are the challenges in power system, why do we go for simulation, and like what all the benefits of having a simulation or a real-time simulation. Now let's understand what is real-time simulation. So what exactly do we mean by real-time simulator? So just it gives the good result at the right time? No. So real-time simulation basically means we obtain determinism in our results. Like for example, if I say like we want to send voltage and current signals from our power system network in a virtual environment to an actual relay at t equal to 20 seconds. That means the relay should accept the voltage and current signals at t equal to 20 seconds so that it will be able to operate. The hardware devices are always synchronized to a physical clock. The physical clock means nothing but your wall clock or a wristwatch. Okay, so the real-time simulator is actually synchronized to that particular wall clock. So when we are running our model, the simulated MATLAB model on a real-time platform, the results that we will be obtaining from the simulated platform will be actually synchronized to that physical clock. So if I say at t equal to 10 seconds, the fault has been introduced. That means at t equal to 10 seconds, the fault has to introduce, and t equal to 10.1 second, the voltage and current has to be measured and sent to the relay. Then at t equal to 1.5 at 10.5 seconds, the relay will send back the trip signal. So this is how they have to operate in a synchronized manner. For example, most of us have seen MATLAB models. Okay, so there's something we mentioned on the top. There's the execution time for the model. Okay, when you start execution, when you press the play button on MATLAB, so you actually see on the bottom like how it actually operates. So when we start the model execution, the model can actually, so for example, we are mentioning 10 seconds for model execution. Now we started the model execution. Now we can actually see, we can actually notice that the model for 10 seconds may get over or at 10 minutes or it can get over in 1 second. So it all depends upon the complexity of the model and the type of solver which we use inside our MATLAB environment. So this simulated platform actually it overcomes all these challenges. Okay, so it doesn't depend upon the timer of the host PC. It has a timer which is synchronized to the physical clock, so which will help you overcome such challenges and help achieve real-time simulation. At t equal to 10 seconds, the model has to get over its execution. That means at t equal to 10 seconds, it will get over. So obviously, we will be getting good result, accurate results, and at the right time. So the real-time simulation is required when the real hardware is connected to the simulation platform. Otherwise, it ensures coherent time response, that is, as I said, determinism is obtained with real-time simulation. Then the third advantage is it allows the simulation to lure the real hardware. That means even if you don't have a relay, we can actually take a protection logic and we can run inside the real-time platform in parallelly in like simultaneously with a power system network. So you are actually luring an entire power system network along with an hardware relay. Now, so talking about real-time simulation. So this real-time simulation basically works on fixed step simulation. So in MATLAB, since we are dealing with MATLAB platform, Simulink platform, so I'll be talking about MATLAB design parameters. So in MATLAB, if you go in the configuration settings, you will be seeing there are two types of solvers used, fixed step solver and variable step solver. Real-time simulation is only about fixed step simulation. So we will decide a fixed time step for the entire model. So when we are deciding a fixed time step of the entire model and we are setting the execution time as, for example, 10 seconds, then we can calculate like the number of samples are being generated of equal sizes. For example, we are deciding a time step, fixed time step of 10 microsecond, and for example 10 second is the total execution time period. That means the number of samples of equal duration generated are 10 seconds divided by 10 microseconds. So that is the number of samples that are generated, and those samples will be used at the back end to regenerate the results. Okay, so the figure shown here, it shows that when we are performing a real-time simulation, what will happen is within this fixed time step, the entire model that have been designed will be computed, the results will be taken, and the commands will be generated. So this process will happen for every time step. As I said, if you are running the model for 10 seconds and the time step is 10 microsecond, so for every time 10 microsecond up to 10 seconds is over, this process will be repeated. Okay. Now, what will happen like if this process is not proper or if real-time simulation is not achieved? Like how will you identify that real-time simulation is not happening? So basically what you are going to see here is shown in this next slide. So here you see the fixed time step which we are talking in the previous slide, for example 10 second, 10 microsecond. So the model is not able to complete the entire execution within the 10 microsecond. So what it needs is increase the time step for the model. That means if you make the model run for 20 microsecond, okay, then this entire process can be computed within that particular duration. So that means the time step has to be increased to achieve the real-time simulation. But whenever there is such a error or like warning is coming, we will see something called as an overrun. Okay, so there are specific options where you can actually monitor such overruns in real-time simulator platform provided by OpenRT. So we'll be discussing in our later slides about that. Now, so this is basically this entire part one of Agile for Power Systems was about benefits, challenges, and the need for real-time simulation and what exactly real-time concept means. So in the next session, we'll be dealing with hardware architecture. So see you again in the next session.